Here we go. Introduction to Algorithms, Chapter 1. I'm going to probably not be typing too much today, so I'm going to move my keyboard, and we will basically read, and I will essentially take notes on what we're talking about. And then once we get to like an actual programming problem, we'll do it. I literally have no idea. I think that the book is in like some pseudo language. Let me find an example. Yeah, like it's in like this pseudo language. Let me show you. So it's like 4 I equals 2n p equals a I, etc. So it's just like this pseudo-y language for writing the algorithms. So nope, not in Java, which is arguably nice for me. Um, okay, cool. So the first chapters of these books are always pretty boring from a coding standpoint. It's mostly just going to be me like writing and reading. So sorry, that's just how the first chapter always goes. All right, so an algorithm is any well-defined computational procedure that takes some value or a set of values as input and produces some value or a set of values as output in a finite amount of time. Okay. And the algorithm is a sequence of computational steps that transform the input into the output. You can also view an algorithm as a tool for solving a well-specified computational problem. Okay. So we have like a statement of problem, specifies in general terms a desired input-output relationship for problems. And these could be of arbitrary size, and the algorithm describes a specific computational procedure for achieving that input-output relationship in all problem instances. Okay, so let's define. Okay, so we're going to formally define a sorting problem. So sorting problem. If you have trouble hearing me, just let me know. Yeah, it's like Python-like, agreed. Let's see how you do doubly linked lists in safe Rust. That's fine. I mean, it doesn't need to be necessarily safe. Hey, Abby, how's it going? So we have like formally, yes, we have an input, which is like a sequence of n numbers. Okay. Output. Oh, and actually, that's kind of interesting. Like doing the doubly linked list thing means that I'll have to touch unsafe Rust, which is arguably a good thing as well, because I would like to learn this. A permutation. Oh, they're using these like angle brackets. I don't really know the notation here. Okay. Such that other way. Okay. So A1 prime is the smallest or equivalent to the next one. Okay. So I'm not going to show the example. Like, I think that just showing these two things should be obvious enough what like a sorting algorithm is doing, and also, like, most of us have done this kind of stuff before, so hopefully, that's obvious. Okay, so like instance is a like specific input set. Okay. Let me see if it. Yeah, the input sequence. Not set. Okay. So that's an instance. An instance of a problem consists of the input needed to compute the solution to the problem. Okay. Yeah, sorting is a fundamental operation in computer science. I think this is obvious. Because of this, you have a good number of sorting algorithms at your disposal. Which algorithm is best given for a given application depends on many factors: the number of items, the extent to which the items are already somewhat sorted, um, restrictions on the item values, the architecture of the computer, the kind of storage devices, etc. Okay. An algorithm for a computational problem is correct if for every problem instance provided as input, it halts. In other words, it finishes computing in a finite time and outputs the correct solution to the problem instance. And a correct algorithm solves the computational problem. Okay, interesting. Definitions. An incorrect algorithm might not halt at all on some input instances, or it might halt with an incorrect answer. Uh, Contrary to what you might expect, incorrect algorithms can sometimes be useful if you can control their error rate. We'll see an example of an algorithm with a controllable error rate in Chapter 31 when we study algorithms for finding large prime numbers. Interesting. Okay. Okay. Interesting. So this section is probably not worth reading out loud. So I might skim it and just like say some things. But basically, he says what kinds of problems are solved by algorithms, and I feel like lots of them are. So here's one of the examples it comes with is in the Human Genome Project. Like there's obviously a ton of like data analysis, and they use sophisticated algorithms to like do uh, gene editing and matching and whatever else they do with DNA. Um, Things like searching up directions on the web use clever algorithms apparently. Um, yeah, cryptography, obviously, manufacturing, shipping, flights, etc. Uh, yeah, okay, cool. So there's a bunch. Um, like this is like talking about mechanical design and like reusing parts and like finding parts that would fit, or like the kinds of things that could be made with the parts that you have or something. Um, an image representing like a cancerous tumor or something, compression, etc. Okay, so there's a lot, is the point, and that like only scratches the surface. Okay. Um, so it says the list above is far from exhaustive, but they exhibit two characteristics common to many interesting algorithmic problems. They have many candidate solutions, the overwhelming majority of which do not solve the problem at hand. Finding one that does, or one that is best, without explicitly examining each possible solution, can present quite a challenge. And they have practical applications. Okay. Do 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 do. Okay. Uh, So then it says like data structures. So we're also going to talk about data structures. It's just, I think most of the people watching this will be, this isn't bad handwriting. This is pretty decent handwriting. It also doesn't come up super well because like I have so much stuff in front of me. I think we're mostly familiar with data structures, but they're going to talk about some of them and like how to do them, which is like something that I don't know how to do. Like I tried to do red black trees in Haskell at one point, and I failed miserably. I didn't really get it at the time. I tried reading a paper too, and I still didn't get it. So hopefully, like we can learn a bit more and then be better at that in the future. Okay. So it says, although you can use this book as a cookbook for algorithms, you might someday encounter a problem for which you cannot readily find a published algorithm. Um, This book will teach you techniques of algorithm design and analysis so that you can develop algorithms on your own, show that they give the correct answer, and analyze their efficiency. Yeah, these are the kinds of things that I want to be able to do. Um, and like we have all the pieces to set that up. It's decent. Okay. Um, yeah, so there's like it basically says there are cases where we look at like specific problems. There are cases where we talk about more general things like conceptually, like divide and conquer, and then like dynamic programming and amortized analysis. Okay. Most of this book is about efficient algorithms. Our usual measure of efficiency is speed. How long does it take to produce a result? And then there's one chapter 34 studies an interesting subset of these problems, which are known as NP complete. Uh, why are I don't actually know what an NP complete. I've heard the term NP hard before, but I don't actually know what it means. Um, so although no efficient algorithm for an NP complete problem has ever been found, oh okay, well, nobody has ever proven that an efficient algorithm for one cannot exist. I love this. I love problems like this. Nobody has ever proven that an efficient algorithm for one cannot exist. There's stuff like this in quantum theory too. In other words, no one knows whether efficient algorithm exists for NP-complete problems. Okay. Um, they also have a remarkable property that if an efficient algorithm exists for any one of them, then efficient algorithms exist for all of them. Sorry, I need a drink of water here. I absolutely love that. This sounds exactly like the kinds of things one does with the exact density functional in quantum theory. It's like we know all these properties about these things, but we don't know how to find them. It's like, how? How do we know that? That's amazing. I love that very much. Okay. Uh, this relationship among the NP complete problems makes a lack of efficient solutions all the more tantalizing. Agreed. Third, several NP complete problems are similar but not identical to problems for which we do know of efficient algorithms. Computer scientists are intrigued by how a small change to the problem statement can cause a big change to the efficiency of the best known algorithm. Okay, so you should know about these problems because they arise surprisingly often in real applications. It just it says if you come across one of these, you are likely to spend a lot of time in a in a fruitless search. If instead you can show that the problem is NP complete, you can spend your time developing an efficient approximation algorithm. Not like the best or perfect, but it gives good. It's possibly good. Okay. Yeah, so I guess a good example of this is the traveling salesman problem. Is NP complete, and so I think in most of the traveling salesman problems, we just use like Monte Carlo algorithms to basically just sample the space and then pick something that's mostly correct, right? Okay. So alternative computing models, um, it's basically talking about Moore's law, like you know, if you're unfamiliar with Moore's law, the basic idea is clock speeds for computers increased, like doubled every year. So for a while, for a long time. And so you could keep the same exact computer code and it would just get faster every year. But we're at a place now where Moore's law is no longer true. And so people like to say there's no more free lunch. I don't really know who coined that term, but that's the term I hear all the time. And so algorithms and like being efficient is way more important than it used to be. Well, you had to be efficient in other ways before, but your cores got faster and faster every year. uh, my allergies are going a little bonkers right now, so I'm sorry if I'm sniffly. Okay, and then basically it's just pointing out that in chapter 26 we're going to talk about like parallel and concurrent programs and algorithms and things like this, which would also be interesting to learn. Like I did parallel and concurrent stuff before, but not from like a data structures and algorithms standpoint, which I think will be really cool. And then they also talk about like online algorithms, which I guess are like streaming algorithms. It says algorithms that receive their input over time rather than having all the input present at the start. So it sounds like streaming kind of thing to me. Would also be interesting. Okay, so the best part about these books is they come with exercises, and that's kind of like what I like to do on the stream is do the exercises. So let's see. Um, these ones are not going to be very interesting, um, just because like we haven't done any algorithms yet. So, so this one says, describe your own real world example that requires sorting. Describe one that requires finding the shortest distance between 2 points. I don't want to do these. Um, real world example of sorting. I would like to organize all of my videos by time. Like, yeah, sure. This one's more interesting. Other than speed, what other measures of efficiency might you need to consider in a real world setting? Like memory efficiency, for example. I think that's like, or scaling with input size, things like that. Although I guess that's kind of still speed, right? It says select a data structure that you've seen, discuss its strengths and limitations. Um, well, apparently you can't implement a doubly linked list without unsafe rest. So there you go. Okay. I don't really want to do these. Okay. Algorithms as a technology. If computers were infinitely fast and computer memory were free, would you have any reason to study algorithms? The answer is yes. If for no other reason, then you'd like to be certain your solution method terminates and does so with the correct answer. Okay. These are kind of obvious. Okay. So efficiency. Different algorithms devised to solve the same problem often differ dramatically in their efficiency. Chapter 2 introduces two algorithms for sorting. The first, known as insertion sort, takes roughly equal to C1 n squared to sort n items. Okay. Where C1 is a constant that does not depend on n. Okay. That is, it takes time roughly proportional to n squared. The second, merge sort, see, that was bad handwriting. C2 n log n. I'm gonna use parentheses just to point out like it's a log. Log 2. Okay, and C2 is another constant that also does not depend on n. Insertion sort typically has a smaller constant factor than merge sort, so the C1 is less than C2. We'll see that the constant factors can have far less of an impact on the running time than the dependence on the input size. Let's write insertion sorts as C1n times n and merge sorts runtime as C2n log n. Then we can see where the insertion sort has a factor of n in its runtime. Merge sort has a factor of log n, which is much smaller. So as an example, when n is 1,000, log n is approximately 10. And when n is 1,000,000, log n is approximately only 20. So insertion sort usually runs faster than merge sort for small input sizes, and that's just because of the constant factor out front, right? Hey, Gerkus. I'm working with Rust, kind of bashing my head. Came from C++ and C Go land. What are you bashing your head on? Something specific? I'm still learning Rust as well, so kind of a lot of things. Anyway, if we look at this math, if we're talking about small n, the difference between n squared and n log n becomes smaller, and therefore that constant factor out front becomes more important. So if this becomes more important than the n squared log n, then you can see how like smaller problem sizes would make insertion sort sometimes more efficient, if not always. Yeah, and then eventually, once you get to a certain size, the merge sort will always be faster because it's just how the math works. Okay, this shows like a very specific example and then just writes the math out. So it says by you. The point is they basically put a fast computer versus a slow computer, and then show that even for large problem sizes, merge sort on the slower computer will be faster. Let me make sure I understand this. Yeah, so because we're using the algorithm, the more efficient algorithm on like a large problem set, even the slower computer is still like a bunch faster than the fast computer because the algorithm is so much more efficient for large problem sizes. So that's kind of the point. Yeah, this just says like total system performance depends on choosing efficient algorithms as much as on choosing fast hardware. Like obviously you still want the fast computer to run the fast algorithm if you're looking for performance. Okay. Yeah, just commenting. Yeah, that's fair. How's it going? Welcome to the stream. Um Okay, so you might wonder whether algorithms are truly that important on contemporary computers in light of other advanced technologies such as Wait, what? Why are these this is like a weird comparison to me. So it's saying like you might compare algorithms to other advanced technologies such as GUIs, object-oriented systems, integrated web technologies, machine learning, mobile devices. Why would I compare algorithms to those things? I don't really understand that, but okay. Um, I guess they are advanced technologies. Anyway. Um, it's just making a point that like algorithms are everywhere, and you can't escape them. That's basically what it's saying. I don't want to read it verbatim. Okay. Yeah, like this book is trying to convince somebody like what yeah, like what I don't know what object oriented systems have to do with first advanced technologies. Like I mean I guess it's come a long way, but it's kind of confusing to compare those two things. Like I don't know how I would compare algorithms to object oriented programming. Anyway. Um okay, so this chapter here is like trying to motivate you to why you might learn about algorithms. I don't think you need to convince me of that, so not a big deal. Okay. Okay. So this one is kind of interesting, and so I would like to. Am I an algorithm? I would argue that you probably are an algorithm, right? Like your brain is wired up in a certain way and designed to, do certain things. So if you've never used this website, it's actually pretty great. So I'm going to try and use it to plot two functions and see if it works. So we want to plot 8x times x, and we want to plot 64. Oh, I probably want a times here. Times x times log x. Let's see if this works. It does. Seemingly. Maybe if I write log 2. Yeah, okay, that works. Um, I'm not thinking about the shape so much here. Yeah, for it's great for calculus, but general plotting is nice too. So I think what I want to look at is this plot. I don't understand why I'm seeing so many of these. Like, what am I looking at here? This is not like what I asked you to plot, right? And what is this RE? And why is there? I'm very confused. Okay, well, anyway, let's just pretend that this is the right plot, even though I don't think that it is. like is anyway. Okay, let's pretend it's this. I don't actually know. I'm also very confused by this plot here. Uh, also, like I want to show from x to 0 to infinity. So why is this from negative to? Anyway, very confused. Let's just look at this one. Okay, so we can see that for a little while, uh, x. So this is describing the like computational efficiency of these two algorithms, and you can see for like quite a while the insertion sort, which is like it's saying like the insertion sort is 8n squared, and the merge sort is 64n log n. So for the purple line here, we're more efficient until we hit about what looks like somewhere around 45. And then once we hit 45, you'll see that the merge sort is more efficient and also scales way more linearly. I don't. I mean, it's x squared, right? So, or no, it's not. It is. It's closer to linear anyway. So it's going to scale much more efficiently past about a problem size of 45 items. So there it is. But I'm still not convinced that this is the same function, x log x over log x. And I don't really understand where it's getting that. So, like, it says the right thing here. What if I just have one of these? What happens? Yeah, that kind of looks like how I would expect. Maybe if I write and, we probably can do that. Okay, it doesn't like that. Anyway, it is what it is. We might be able to do this in like some other format and it would work, but whatever, it's fine. So I think that's kind of interesting, like just thinking about like the mathematics of this stuff. Um, okay, so then it just asks another question. Actually, interestingly, it has a table that you can fill in, which is kind of interesting. Okay, so chapter 2. This is called Getting Started. And I think getting started is probably going to be more interesting because we're going to have like actual stuff to do. I just need to edit the stream info. Chapter 2. Started. Done. Okay. This chapter will familiarize you with the framework we'll use throughout the book to think about the design and analysis of algorithms. It is self-contained, but it does include several references to stuff later. It also contains several summations. Appendix A will show you how to do that. We'll specify algorithms using a pseudo-code that should be understandable to you if you've done computer programming. We'll see why insertion sort correctly sorts and analyzes its runtime. Or sorry. Oh, why it correctly sorts and analyzes its runtime. Okay. And we'll probably do some Rust programming when we see this when we see this example. Following a discussion, we'll use a method called divide and conquer to develop a sorting algorithm called merge sort. We'll end with an analysis of merge sort's runtime. Wonderful. Okay, so we already talked about the sorting problem. We have a sequence of n numbers, and then we permute them such that the lowest one is the first one, and it's ascending. Okay, so there's some terminology here. So numbers sorted are called keys. Not heard this term before. Okay, so it says when we want to sort numbers, it's often because they are the keys associated with other data, which we call the satellite data. With who else? Satellite data. Together, a key and satellite data form a record. So it's a map or record. We all know this, but key points to satellite data. Maybe we don't all know this. I'm not sure. Consider, okay, we don't need to see an example. Okay, so like it's pointing out, like, let's imagine if we had a spreadsheet, um you know, we could sort a key and then we'd have the satellite data associated with said key, so we can sort that as well. Yeah, they're using a pseudocode. They point out that it's similar in some respects to C, C++, Java, Python, or JavaScript. And then it says, apologies if we've omitted your favorite language. We can't list them all. That's true. There's so many. Okay. We start with insertion sort. There's just like, sometimes I have to like read paragraphs and see if there's anything useful in there. Yeah, this book is like super common for those, by the way. So it's this book now. This is the 4th edition of the book, but there's like a ton of different versions. Um, well, there's 4 to be exact. Okay. Okay, so let's do some coding because I like coding. So we have I have this pseudocode here. Do you want me to write the pseudocode that they have, or do you want me to just convert it to into Rust and be done with it? Actually, this book came. Kind of don't have enough desk space to do this because I can write the pseudocode here just so you can see what it looks like if that's at all interesting. I think I'm going to do that in case somebody is like interested in potentially getting the book and they would like to know what this looks like. So this is the insertion sort. They label it AN, not exactly sure what that's about, if it's like some notation that I'm unfamiliar with yet. So we're going to say I equals 2 to N. Key equals A, which I'm assuming is a vector of letters. So then it says insert A sub I into the sorted subarray A1 to I minus 1. So we have J equals I minus 1 while J greater than 0 and a J greater than key a J plus 1 equals a J equals J minus 1, and then a key. Okay, so now we have the pseudo code there, and then we can write Rust code from there. So I've set this up. Wait, what? Oh, that's why. So I've set this up such that each chapter can have its own Rust file like this, And then also if we decide that we want tests, we can also make chapters chapter 2 test rs. And there's like some way to basically include this chapter no test like that. So if we decide we want to do tests, then we can do that like this. And there's also example tests. Okay. If you have questions about the code, please ask. Otherwise, I'm just gonna go for it. So, my understand. Oh, well, maybe I'll just say my understanding is that this basically says go look in this file for tests. So the compiler will look at chapter2.rs and say, you need to go see this file for the tests. And also, it's pointing out like this these tests can use this for functions. And then this like use super star thing says anything from chapter 2 can be used here. So it's like this weird sort of cyclic nature that allows you to do this thing. Anyway, so we're going to have a pub function. It doesn't necessarily need to be pub. You can do private and public tests with this style if we wanted to. But maybe we want to use this later. So we're going to call this insertion sort. And it's going to take like, we'll just use the terms here. So I'm going to take an A. That A can be, I guess, like a slice T. So this is generic over any T, I think. I think we need to be able to compare items. So there might be a like a trait that T needs to implement to compare things. And then this thing's going to produce, sorry, arrow, I guess, a list of T. Is this valid code? Not sure. Okay, so for I. N is this appears valid. And oh, actually we're not going to return anything, are we? Because we're modifying A directly. So, this is going to be like this, I think. Okay. So we're going to say we don't really need to pull out key, do we? It's always going to be A sub I because everything uses J there. So here we're going to have a mutable J. Yeah, standard compare. Does it have a trait attached to it? Okay, perfect. So, standard compare Rust. Eek. Okay, so this thing needs to implement board, I guess. Probably. So this thing is going to probably be some kind of integer. I don't know what though. Maybe it's just a U size, and it can start at 0. Okay. And then let's put like key equals AI like this. So we don't have to, like, there's no reason for us to have that key there, I don't think. All right. Do we have while loops? So J is greater than 0. Hey, Aldrin, how's it going? Hey, Detox Mango. That's a great name. How's it going? And AJ greater than AI. J equals J minus 1. I have no idea if I can do this yet. Is this Corman? Is that the right author? Yep, Corman. It's a EN just for reference, but I didn't actually know that until I looked. AJ plus 1 equals AJ. Oh, we need like a ton of these. I'm wondering if I can find a fellow programmer to build a crypto. I don't even know what that is. And I don't think you're going to find anyone that wants to do that kind of stuff. What I don't know what HFT is. What is HFT? Is this cryptography or like crypto? Because if it's the latter, you're not going to find them here. Yeah, you're not going to find that in my channel most likely. I'm very uninterested in that stuff. Okay. So I 2 to n. I have no idea if this will build. It seemingly will build, but I think that's only because I'm not including this in librs. Oh, I see. I need to include it in chapters. And then we say pubmod chapter 2. And the reason that I need them to be public is that okay, so now we're going to get problems, which is probably good. No, maybe you will find that here. Why isn't it? Okay, here we go. Nice. I know Haskell. All right. Now, this is where Rust is going to be kind of a problem, right? So we need to learn how to deal with this. One thing that's kind of interesting is that this is here, but we probably don't even need that to be there. And we can probably just say this. All right. So we need to be able to like get this thing. So this also needs to include that other thing that we had before. I think we had this in the benchmarks somewhere. Copy, yeah. So this thing needs to have ord and copy. Oh, this is a reference to T. Okay. Let me see. Right. Thank you. I need at mute. And do I need a vector? Oh, apparently I do. Okay. So back. Yeah, still like learning what types I'm supposed to use here. Is this not how you do like multiple? Okay, so I'm not changing the length. I don't think. Because well, it doesn't know that I'm not changing the length, it seems. Use a plus. Ta-da! Okay, thank you, Isitsu. You've helped me a ton already. Okay, so what did we learn? We learned that you can't use slices to mutate like arrays. You should use I don't know what the syntax is for Rust like docs. Mute vec t. And we'll start like this. Okay. T is almost always going to need board plus copy, likely, when we're doing I can use okay. Well, let's try that next. It probably was just because yeah, it seems like it's fine. It was probably because I was using the comma and it was like, what do you mean? But I have to think about it as like a union or something of abilities or traits or whatever. Okay. Board plus copy for sorting. What else did we learn? Actually, I think this is some Rust stuff too. But I think if we say this and then try to use this here, it would be fine. But like, it's kind of like a pointless thing, and hopefully the compiler would just like optimize that away. And because we don't use, if we had to use a sub I down here, I think that it would be pretty unhappy. Like if we made this key, oh, it seems fine. And that's probably because we're doing app mute slice or whatever. Anyway, we don't really need this. Let's just leave it there. It's fine. Like, doesn't really matter. Okay, now question, is it correct? Let's get rid of this and this. Okay. So function. I have to annotate this, I think, with something. Sorry, it's gonna take me a while to get used to these. Okay, just test. Insertion sort works. This isn't gonna take any arguments, and we're just gonna say assert equals insertion sort at vec 5, 4, 3, 2, 1 is 1, 2, 3, 4, 5. Missing tokens in macro arguments. Isn't this how you make a vector? Oh, I probably need to do that here too. How is this unused? How would you get insertion sort if expected end of macro invocation? Okay. So Rust construct vector. It might be because of the way I have insert equals. Assert equals. End there. I don't understand. I'm pretty sure there's a macro to create these things, right? Do I have to like include something? Oh, okay. That could be. So let's say A unsorted is vec. Well, let's use like the terms input, output. Okay, input, output. Oh, duh. Okay, so actually also this is kind of wrong. So because we need to do insertion sort at input. Is this because I'm not passing like a slice? Is there like a... That's not going to work either. Oh, I actually have to write that there? Oh, weird. Okay. Interesting. So, is this... If I put this here... Yep. Okay, so it fails there because it doesn't understand unless I put this here. Oh, sorry. Like that. And then this is happy. And then we need to figure out what's going on with this assert equals thing. Oh, it's just I have this written wrong still. Input, output. Sorry, I totally missed that. Okay, so this is interesting. So we, again, a lot of this code is going to be pretty impure like this. And I need to, yeah, I definitely need to spend more time. My little thing went to sleep, so that's why you see press button to continue. So we create the mutable input. We say like, look, you need to pass a mutable reference to this thing. I kind of like this actually because you're saying like, look, this thing is producing side effects, and you have to be very clear about that. Um, I like that a lot. Like you can't just say you can't just put input here and be happy. It's like there are two places that are telling you, hey, insertion sort is doing side effects. I kind of like that actually. Okay, so let's see if this works. Cargo test. It does not work. So something is wrong either with the way I transcribed the algorithm or the way I wrote the code. So uh oh yes, I forgot to store the thing. So at the end of the for loop, we need to say a j plus 1 equals key, like that. So I missed that part of the algorithm. And then cargo test. Thank you for pointing out the bot so I can ban it forever. Does the macro compare? Oh, that's a. I think it does. Because it says like if you look down here, it says like left is this thing, right is this thing. So you should be able to see that. Wait, sorry, what? Corman is a great book. I had a dream of implementing all the algorithms in Haskell. That's kind of like where we want to go. Uh, your drawn algo uses. Yep, you found it. There's the bug. See, this is one of those things, line 12. Thank you for pointing out. The line is very helpful. I actually don't use relative line numbers because I find it really hard. So there it is. So I think that's the bug. But because it starts at 2, that's the part I'm unsure about. And I think this is really supposed to start at 1. That doesn't change anything. So I'm a little confused by this. Maybe I didn't save. Maybe the point is there's an edge case here. Um, could this be like a 1 versus 0 thing? Yeah, that just straight up panics, which is kind of funny. So it does most of them, just doesn't do the first one. I think if we didn't have the largest element in the first spot, would this do it? But like obviously that's not. Nah, it just doesn't even touch the first element. So anyway, I need to go, but this is like the first thing we need to fix. So there's gonna. It looks to me like it's very possible that we're gonna have to like think carefully about indices when we're doing these. So Altern, I want to do both. Like I would really like to have. Oh, I'm sorry, Garricus, I totally missed your follow a while ago. I really appreciate that, but I see you're still around, so hopefully you saw that. It should have popped up on the screen too, which is nice. Um, so it's probably because this needs to be. Yeah, I'm kind of like I'm trying to focus when I do this kind of stuff. That's probably what we need, so it doesn't panic. Nah, it still panics. Attempt to subtract with overflow. Ah, here, because we're using use size. Um, oh, but then we can also say 1, I suppose. See, I haven't done for loops in a while. You can see I'm having trouble with this. But this will at least get all of those in order. It just doesn't touch the first one. And that's because this can't be 0 because this j has to be I minus 1. So, yeah, anyway, so there's like a subtle bug here where um oh, we do there could we just like specify the type here? We probably have to cast them though, right? Somehow. The problem is I don't know how to do this. Like this can really just probably be like an I8. But I don't really know how to do that. Oh, as. We probably don't need that much precision. Yeah. So because you only want to ever access them as a U something. So like you need to say that like you basically I think need if I equals 1 or sorry, if I equals 0 uh 0 else. And then maybe you can start at 0. No. I'm not really sure. So this is kind of why I don't like code like this. It's kind of hard to think about. Well, I don't think about it very often. So anyway, we just need to like figure out what's going on with these indices and go from there. But for whatever reason, we don't touch this first one. It gets everything else, but it just doesn't touch the first one. And I'm wondering if there's a better way to fix this. Or if this one is purposefully broken. You know what I mean? We could also start like printing stuff to see what it's doing each loop, but anyway, we'll get there next time.